So the total radiation is made up of the contributions from all of these different infinitesimal current elements. But what is the contribution from just one infinitesimal current element? Can we figure that out? By the way, these are also called a hertzian dipole. So we got to set up that radiation integral to find it. But let's draw a picture of what we're talking about. Here's our coordinate system. Let that be the z-axis there. And we're going to assume that we have a very short element of constant current. And that's the total current, I naught, and it has cross-sectional area S. So our volume current density, J, is going to be Z hat I naught over S for Z within the range minus L over 2 to L over 2. So its total length is L. And now here's the thing. This is an infinitesimal current element, so L is very small. And S is very small. And we've said that the current is constant on this current element. Otherwise, it's not really useful as a building block for integration. If we set up our radiation integral under those constraints, we got mu naught over 4 pi, just like we normally would. We got the integral from minus L over 2 to L over 2. Now, since our current is constant over the cross-sectional area, dV here, or dV prime, just has to be S dZ prime. Then we've got Z hat I naught over S e to the minus j k r minus Z hat Z prime over magnitude R minus Z hat Z prime S dZ prime. And now here's the thing. We just said L is very small. How small is it? L is so small that this term is constant. Over its length. That's what infinitesimal means. So if that is the simplification we can make, then we've got that the magnetic vector potential due to this hertzian dipole is mu naught over 4 pi. This Z hat just moves out to the front. I naught over S times S, so the S's cancel. We integrate I naught dZ from minus L over 2 to L over 2, so we got I naught L. And then we got e to the minus jkr over r. That's the magnetic vector potential due to a hertzian dipole. And this, like all other radiation integrals, the result is only in the unprimed coordinates r. It doesn't have any r prime or any z prime, theta prime, anything like that. Just r prime. Or just r. Now that we have the magnetic vector potential, we can find the magnetic and electric fields due to this dipole. I'm going to write down the equations for finding them, but I'm not going to write them all the way out because those are in the handout and I don't want to spend a lot of time for you to have to listen to me do it. So we can find that the magnetic field due to this dipole is 1 over mu naught times the curl of A. And the electric field due to this dipole, or really due to anything that has a magnetic vector potential, is 1 over j omega epsilon naught curl of H. So that lets us find the fields for this dipole from its magnetic vector potential. Nice. Now what I want to point out here is that this vector potential has this e to the minus jkr over r term in it. And that term is also going to show up in the electric and magnetic fields for the dipole. That term is very important and special, and it has a special name. It is called the spherical propagation factor. And it shows up in all fields from finite sources. In this particular form, we have to say that it's time harmonic. But there's a similar thing that shows up in time domain sources too, so you don't get away from it ever. So we've got e to the, let's look at it, e to the minus j k r over r. This 1 over r term is going to describe the amplitudes decaying as you move away from the source. And this e to the minus jkr looks like the phase propagation factor from a plane wave, except this one doesn't have planar phase fronts. It has planar phase fronts that are surfaces of constant r. A surface of constant r is otherwise known as a sphere.